So a very good morning to all of you. Hope I am audible to all. Uh, I welcome you all on behalf of Space Society of Mechanical Engineers for a talk on additive manufacturing for aerospace components by Dr. Govind, General Manager MMA, Vikram Sarabhai Space Center, ISRO. So this is an initiative by Space Society of Mechanical Engineers under the SSME webinar series 2021-22 on current trends and advances in mechanical engineering for space applications. So this is our initiative of extending the knowledge in the field of mechanical engineering and materials engineering from the experts in this domain. So we are continuing this webinar series with today's lecture. I heartily welcome you all for today's lecture, and I welcome Dr. Govind, and I would like to give a brief introduction about today's speaker, Dr. Govind. Dr. Govind has done his undergraduate in metallurgical engineering from MNIT Jaipur, and he has done Masters in Technology from IIT Kanpur in Material Science and Engineering. He has completed his PhD in Materials Engineering in IISc Bangalore. He is currently working as General Manager MME Vikram Sarabhai Space Center, ISRO, and he has a vast experience of working in this field for the last 25 years. He is a recipient of INA Young Engineer Award, and is also a recipient of ISRO Team Award. His area of interest are physical and mechanical metallurgy, solidifications and castings, and additive manufacturing of aerospace components. So I will heartily welcome Dr. Govind to deliver a very knowledge enhancing lecture on additive manufacturing for aerospace components, which is also a very knowledgeable topic and very trending topic in these days. So without further delay, I would like Dr. Govind to please start his lecture and give us the knowledge about this. I would also like to tell you that we are live on YouTube, and this lecture will be streaming live on YouTube on the link which was shared. So Dr. Govind, I will welcome you. Please start your knowledge enhancing lecture.
Yeah, just a minute. Thank you, Ankit. And once again, welcome Dr. Govind. I request all the participants to raise their queries either directly after this completing of talk, and YouTube viewers are also requested to type their questions in the chat box. We will definitely ask in the end of the talk. Thank you. Please, sir.
Now my screen is visible.
Yes, sir.
Very nice.
Yeah. Thank you, Ankit. Thank you all for giving me this opportunity. Just bear with me in between if I take some break for sipping water and all, because I'm suffering from some throat issues, COVID-related issues. So please bear with me. So we'll go ahead with this talk on additive manufacturing for aerospace components. This I have prepared about 1 year back, and little bit modification I could do on this talk. So it will cover the basics of all the AM processes, not only on metals but polymers also I've touched upon. And main concentration will be on powder bed fusion, because that process actually has led that particular area actually has led the AM to this level. Okay, so we'll go presentation. So actually in AM now, if we talk about where India is, I'll just like to bring to your notice that India is doing well, and many private companies have come up with very innovative solutions. And here is one, one 3D printer which is based on FDM, which is the largest 3D printer. It can print around 1,000 cubic feet volume, made by the company. And the first print of this 3D printer was a tall, 10 feet tall statue of Lord Ganesha with a footprint of 5 by 5 square feet, weighing 200 kg. Similarly, indigenous metal 3D printer companies come up with the indigenous metal 3D printer, and it has been launched in the market. So Indian companies are doing well in AM, and it is now our duty to take this forward towards application. So where the AM is in metals, AM is there in ceramics, AM is there in polymers. You name it, AM can be additive manufacturing, can be used in almost all areas. It gives the opportunity to print lattice structures, complex shapes, geometries for engines, turbines, in metals as well as ceramics and polymers. Even in composites, AM has been used. In healthcare, it has been used widely. Even in smart structures, where you print AM component, that materials which remembers a shape when they are subjected to some stimuli, and even you can design components in such a way that material will behave as if there is no CPU, based on structural design. So AM gives you ample freedom with that regard. Here is one image of bird toucan. Its beak, which is the longest beak of any bird, a large beak with respect to its body. The body length is 25 inch, 8 inches is beak length, and this it has been a puzzle for many biologists and material scientists, because with such a long beak, how toucan is able to balance his body, because it is very light. The design was so light, and without sacrificing the stiffness of the beak. So which otherwise it is not possible to build. Now with AM it can be mimicked. These kind of structures also can be mimicked. So we come to the AM, what actually additive manufacturing is. As most of you may know, that additive manufacturing is incremental layer by layer manufacturing from a CAD model. You get a CAD model and you slice it, and each slice is deposited at time to build a final structure. The material generally used are powder or wire. Why it attracted our attention is because it gives kind of design freedom which AM gives no other process, and lead time is very short. And there is no compromise in mechanical properties. In fact, we found that mechanical properties are far better. It gives a very good control on materials and microstructure. And actually the process controls now so good that you can reliably get dense part from wide variety of materials without much of a trouble. And AM, which was earlier considered as a rapid prototyping, has changed to rapid manufacturing. It has become a part of reliable supply chain for aerospace. AM in aerospace, you see the most widely publicized GE Aero LEAP engine, where 18 components were converted into single, and the alloy selected was copper chromium. Similarly, the cryo engine thrust chamber printed by Rocketdyne. Then here is example of a bracket, wherein by using fan that is designed for additive manufacturing, the weight of the component could be reduced 40% without any compromise on any mechanical aspects. In fact, stiffness increased by 30%. Complex heat exchanges like this can be built by hand. So You see the conventional manufacturing, how it goes. A designer designs it, gives to a CAD department, they generate fabrication drawing, it goes to materials team, they make a semi-finished material for that particular component, then it goes to fabrication team and the final product comes out. EM demands that all people, designer, materials team, fabrication team should come together to finalize that design, process design, component design, and then a product comes out. So there is a need to have an integrated structural materials design tools, which will accelerate adoption of AM for aerospace design community, and it can come out with an innovative design which can lead to saving energy and the weight. So now they are basically based on 4 different types. These are wet polymerization, material extrusion, powderization is this. We are doing a curing, selective curing. So there are 2 techniques: stereolithography and digital light process. Material extrusion, we have FDM and free-form fabrication. Then powder wet fusion, we have selective laser sintering and material fusion. Material jettisoning is another process. So we'll come to the details of the process. Here is a polymer bath. I believe my cursor movement you are able to see.
Yes.
Yeah. So there is a polymer bath. Laser comes on the laser is exposed on the surface as per the slice, 2D slice, and it selectively cures it. And after curing of one layer, it moves down by a distance equal to the thickness of the layer, and then next process starts. So the adherence of layer to another layer is controlled by the depth of curing, and this process is widely used for realizing polymer components, polycarbonate, ABS, polypropylene. We have used it extensively in making investment casting patterns, and it is a very good tool for that. In digital light processing, process is slightly different than SLA, that is stereolithography. That actually the platen movement is upward here. So part is built at the bottom side of the platen, and bath, the polymer quantity what you require is much less than what is needed in SLA. So light comes from the bottom, and this tank is at the bottom of the tank is transparent to the light. So light is exposed. Light is exposing full layer of the resin, that is photopolymer resin. It is full layer in a one go. Unlike previous case, a laser where laser was tracking the 2D and in a layer the 2D sketch laser was tracking continuously. Whereas here in a one go, full light exposes the full layer, so printing rate is much faster. And as I told you that this, and moreover it uses very common light like LED lamps what we use in house can be used for this. Once that layer gets photo cure, then platen moves up, another one layer of resin comes in and it gets exposed. So this is the way it goes. FDM photopolymer. FDM is a fusion deposition modeling, wherein thermoplastic filaments are used, and here there is a liquefier which is a resistance heated, and filaments are fed to this liquefier, and this liquefier deposits liquid by movement in XY this thing in XY plane, and then once deposition is over in a layer, build platform moves downwards by a thickness of layer, and the second layer builds up. If support is needed, supports are built by support material. So that support material is structured in such a way that it can be dissolved in water. So materials like ABS, PVA, PLA, PC, nylon are built, and FDM is very widely used for realizing many polymer components. Surface finish is slightly poor in comparison to SLA, but its cost is very cheap. It's very very cheap. Compared to SLA patterns, it is less costly and very easy to print. Many companies in India has come up with the FDM machines also. So we come to the selective laser sintering. Selective laser sintering is a process where the laser is used for sintering the polymer powder as per the 2D sketch, and same way the build platform moves, and here a partial melting or partial melt fusion. It is actually the building happens by the fusion of the polymer powder, and we'll come to the multi-jet fusion, wherein layer of the polymer powder is deposited with a fusion agent and detailing agents. The fusion agent, when it is exposed to UV rays, so wherever fusion agent is available, those locations will get cured, and the detailing agent will prevent or control the fusion in the localized location, so that we can get a more close dimensional tolerances. And when we come to the material jetting, here the print head dispenses droplets of photosensitive material that cures under ultraviolet rays, built part layer by layer. So multiple inject print heads are attached to same carrier side by side and deposit the material. So here we can see there are print heads. They will deposit the material, and there is a UV lamp. So as it moves, wherever this photosensitive polymer is sprayed, UV lamp will cure it, and this way, layer by layer, 3D component is built. In metal 3D printer, we have powder bed fusion, direct energy deposition, binder jetting, and sheet lamination. In powder bed fusion, which is known as name of selective laser melting, BMLS, or electron beam melting, here a metallic powder is laid on the print platform, and laser scans as per the 2D drawing, and the build platform moves down. This is and this is how the powder bed fusion builds the metal part. In DED, direct energy deposition, there is a energy source. It can be electron beam, or here it is laser. So there can be two ways by which powder. It is DED powder which we are talking about. So there are two ways by which powder can be fed. It can be like in the center we have a laser source, and from the side deposited or powder is fed to the portion where laser melts the base material, and this whole assembly moves as per the 2D sketch of the plane, and it can be coaxial also. So either coaxial or from the side powder can be deposited. Here we see advantage that we have a multiple feeder powder nozzles. It is possible to deposit gradient. We can build a gradient also in the material by feeding different powders. We have DED wire. So here we have energy source, which is an electron beam or can be a laser, and the wire is fed and it is deposited. So I have one small video for this. Let's see what it plays. So see how liquid is getting deposited on any curved surface. is a part fabricated and is after machining. So these are the various, and this is a binder jet where powder bed is laid, and inkjet printers print head sprinkles binder, and this by depositing the binder only at the location as per the 2D drawing, we build a 3D part, and after completion of the printing, the part is removed. So it is bind. All powders are bind by liquid polymer, and subsequently it is subjected to binder removal and then sintering processes, by which we can rotating sonotron is passed as per the requirement, and wherever it is so we apply pressure as well as ultrasonic vibrations to make a part join at the selective locations. So this way we can build parts. So there are plenty of options available. So when we compare these various ranging from 30 to 60 micron, electron beam allows 50 to 200 micron. So the more the thickness of the layer, larger thickness of the layer, our deposition rate is very high. So we can build part faster, but it compromises with the surface finish. So we'll lose the surface finish part. And DD, like, it allows 250 micron, and DD has advantage because powder size you can control. So it gives you 15 to 60 this thing, and at the same time its deposition rate is almost 10 to 100 times faster, 10 to 100 times higher than the powder bed fusion. And DD EBAM is it gives the highest deposition rate. And electron beams are used, and same way wire also can be used. Arc as an arc source, there also deposition rates are very high, and but surface finish will be poor. There is another part that powder bed fusion size are limited. We can have maximum which is available now is 800 mm. But when we have to build a large part, we have to go for DD, LMD or DD, EBAM or BAM processes. Their sizes you can build larger, but then complexity you have to compromise. So there is if parts are complex, small, powder bed fusion is an ideal technique. If they are large, then we have to go for DD processes. It's possible to have a hybrid printing also. So this is just a glimpse of surface finish what we get. So AM process flow chart, we have just learned about the techniques in powder bed, AM techniques for metal as well as polymers, but how the workflow of AM processes. So first we make a 3D model, then we convert into STL format. Then once the conversion is complete, we decide on the part orientation, how the part is to be printed. Based on the orientation, support generation, the part needs support. The support generation is finalized. Once support generation and orientation are fixed, part is sliced into slices. Each slice, we finalize the tool path, and then 3D printing process is carried out, which after 3D printing, it is subjected to post-processing and inspection. So what is STL format? It is a standard tessellation line-based format. It converts your mechanical engineer, so all of you must be aware of it. The surfaces of 3D model is represented in triangles. So CAD model generally contains the information of geometry and topology both, but STL format carries only geometrical information. So we miss the topological information when we convert 3D model, CAD 3D model to STL format. And each triangle is defined. So in STL format, each triangle facet is defined by 3 point coordinates of 3 point facet and a normal to the facet, which shows the outward direction. So these are the three. This is the facet. These are 3 points, and the normal to the facets defines each triangle. So we try to minimize the triangle because lesser the size of the triangle, better the resolution in the AM process, which you will soon understand how the resolution is controlled here. So we have more data points. If we reduce the size of the triangle, we'll have more data points. So geometry, this topological information which is missing can be contained in geometrical information in STL. STL has its own problems, like problems of inverted triangles, gap, and overlapping. The standard procedure to correct that. So what we lose here is, suppose there is a sphere here, and it has been converted into STL format. So the top curve is the actual CAD model, and when you convert into STL format, this is the triangle which represents the outer boundary. So you lose that information, which is equal to the chord height error. So there is information which is lost when conversion from CAD model to the STL format is equivalent to the chord height error. When once we convert into STL format, and now we go for build orientation. So we have to define that how the part should be built. What should be the orientation? So orientation is basically depends on build time. Actually, orientation governs the build time, surface quality, and support volume. So we want orientation where build time is minimum, we get a best surface quality, and we require minimum support volume. So okay, I'll probably not go in too much of detail of this. So surface quality, build time, basically if suppose there is a rectangle, and if you are building a rectangle in such a way that its largest side is in Z direction, then build time will take more. So you will always want like to have in Z direction, build direction, smallest size. So that is the concept. But there are many other complexities which controls the build time. Then surface quality. Actually, when you divide the STL file into slices, so you get a effect which is shown in the right side bottom. This is called staircase effect, which impairs the surface quality, and it is defined. It is to a large extent controlled by the thickness of the layer. So what it shows is actually if you see that outer side, there is a STL boundary, right? It is shown by the dot line. That is the STL boundary. So and beyond that, you have a CAD model boundary. So that CAD model boundary, when you convert it to STL format, we had a loss, which is defined by the chord height error. Then when further this STL format is divided into layers, we further get a error because of the layer thickness at cusp height. So we the difference between the nominal design and the STL format is chord height error, and is accumulated over the cusp height error. The surface quality of additive manufacture object largely depends on the build direction. If part is straight, then there is no staircase effect. If there is a cylinder we are building or a rod we are building, then there is no staircase effect. But if that same rod or cylinder is tilted by, say, some angle, then there will be a staircase effect. So there will. So these are the. So how we estimate it. So there is the angle between the facet normal and the build direction actually gives us an idea how is the surface quality. And based on the this orientation, support volume also comes into play. So based on these three important parameters, the build orientations are defined. Then how to generate some support. So once we had a 3D model, we converted it to STL format, and from STL we came to defining the build orientation. Once build orientation is defined, then we have to generate the support. So why support generation is needed? Material in each layer must be connected and supported fully or in part by the previous layer to generate 3D part. Otherwise it will sag or collapse. So there can be natural supports, or we have to build the support. So if you see the right side, rightmost image, there is wherever green portion is shown, that is a self-supported structure. To that level, you don't require any support. But beyond that, if when we are building, we require a support. Otherwise, it will sag, it will get distorted, or build will get collapse. Similar way that hand shape, when you are printing, support is needed at the island location. So 3D printing software generally generates support automatically. The criteria for finalizing a support are, it should be easy to remove, less build time, and less volume. The least material consumption should be there, and as well as machine time also should be less. Moreover, the post-processing time also should be less, because the support material we have to detach from the part in the post-processing operation. Once we have generated the support, we have defined the build, this thing, then we come to the slicing. So whole 3D model, which is now in STL format, is sliced into layers using uniform or adaptive slicing techniques. So here at the right side bottom, you have an input model with a crescent moon. And if we go for uniform slicing, we end up shape as shown in the immediate next image. But if we go for adaptive slicing, we are able to replicate the moon shape very closely. The point, what we have done here in adaptive slicing, wherever curvature is more, the slicing thickness has been reduced. Where curvature, the portion was straight, slice thickness has increased. So, but most of the AM processes use uniform slicing. The problem is that there are problems if we go for adaptive slicing, then material delivery system has to be controlling accordingly. Wherever thicker the layer, more material has to be deposited or delivered, and where layer is thin, we have to deliver less material. That is one problem. Second problem is if we are using when layer thickness is more, the energy input to melt that layer increases depending on the, or changes depending on the layer thickness. So these kind of algorithm has not come up yet. That is why most of the PM processes use uniform slicing. So slicing plane cuts when we slice STL format, the slicing plane cuts the edges of triangle of STL file. So here triangle edges are cut. So this coordinates of the edges. The coordinates of these points are calculated using coordinates of vertices of the edges. And now 2D contour is generated by connecting these intersecting points consecutively in a linear fashion. So now we once these STL triangles are cut by a slicing plane, we get points, and these points are connected linearly. So this is a contour which is ready for printing. But there is a problem. The problem is that from one point to another point, the connection is straight. Now another point, there is another straight line. So when an energy source moves, it becomes a sharp changes from one point to another point. There are a lot of zigzag changes. So this motion is not, we are not comfortable with that motion. So what happens is that it is this whole contour is smoothened by curve fitting, and which gives us opportunity to control the losses what we had in chord height error, and we get a more smoother contour with lesser lesser points also. Now points also can be reduced. So this contour is now used for generation of tool path. Next we go for now. So we had STL format, orientation build-up, support, this thing, slicing. Now each slice we have to have a tool path. We have to define a tool path. How energy source should move on that path to generate the product. So now we have a leaf shape figure here. Suppose that our section is a leaf shape, this thing. So the black spot shows that starting of the energy source, and it moves and it ends at the blue. Then this particular portion, this blue to this blue, it moves without causing without giving any energy, then further moves melting and ends up this. So this is an infill path in the figure. In addition to that, we have to do a contour scan. So whole outer profile is scanned by the contour scan first, or it may be a last operation depending on what we choose. So there are infill scanning study and then contour scan. So both the scanning we have to do. And now the process controls are so good that we can get fully dense part, and we can control the microstructure and properties. We can minimize build time and residual stress. So these all options are available, and I mean these processes gives ample freedom to control these parameters. So scanning studies, and infinite scanning studies, there are many scanning studies are available. So I'll not go in details of that. It has its own advantages and disadvantages. So now there are many AM materials. Now what AM did, I mean additive manufacturing processes, this inventors initially they worked with the materials, commercially available materials, which were being used. That was the easiest thing for them to do, and they and all process parameters for these conventionally available materials were developed. Even some newer materials, process parameters have been developed, but I strongly feel that soon, as we have, there are cast alloys, there are wrought alloys. Same way we have AM alloys. The AM alloys, which will compress many of the conventional materials, as well as there will be new materials which cannot be processed by any other processes, which can be processed only by AM. So, research, it has some inherent advantages. AM, because of this inherent processing advantages AM gives, it is possible to design alloys which we were not able to do it because conventional processes it was not possible to process those alloys. So now it is possible to process those alloys, and people are coming up with many new compositions which are possible to process only by AM, and they can give a very fantastic combination of properties. Now, because my talk will be more on powder fusion, so now we understood the processes. Now, how the flowchart goes in. The first is comes this powder. For powder fusion, we require powder. The powder making processes, as most of you know, the gas atomization process, where a liquid is metal is melted in a crucible, and it is allowed to fall through a nozzle, and gas, either argon or nitrogen, is impinged on the falling liquid, and at high pressure, causing it to break into small droplets which solidify during their flight in the chamber and gets collected at the bottom. Then rotary atomization, the molten metal is poured on a rotary disc, and when molten metal drops or fall on the rotary disc, it flings away from the disc as a small droplets flings away from the disc and solidify and collected in the at the circumference. Then plasma rotating electrode processes. It is widely used for reactive materials like titanium, niobium, and all that thing. And here, an electrode of the material is melted by plasma or the thick arc, and then it is rotated. So there is a central action on the droplets which are forming at the arc location, and it is ejected out. And during flight, it gets solidified and then collected. So these are the pictures of the powder, what we get from these processes. First three images on the top are gas atomized. Then in middle we are having a rotatory atomization, and then prep process. These things, all these processes, powders are being made and are being used in AM. So once we have a powder, now what kind of characterization we have to do, means whether any powder is okay for us, or what kind of characterization we should carry out. So first thing is that what we want. We want that in powder bed fusion, when powder is spread on the build platform, its density should be highest first. That is all. That is the aim what we are having. So for a given layer thickness, how to get the maximum packing density for the powder. So then the question becomes, first question comes, what should be the preferred powder size? So what literature says that the finer the powder, low is the packing density. So fine powders generally gives a lower packing density. So should we go for larger and larger particle size? So and then that is one part. Second part is what should be the shape. So shape generally spherical shapes gives us the best packing density. And what should the particle size distribution? So there is in powder metallurgy there exists a very good correlation wherein it is found that 75% of the large and 25% small powder, if we mix, it will give the maximum packing density. But in AM we don't and in powder metallurgy you have ample opportunity, ample things to compact the powder, and all those processes are there. But in AM we don't have those kind of things. So that in AM it is it those kind of things can be directly taken to AM is the question mark. So there were many studies done. I'll not go in details of that. We'll directly come to the conclusion. So the powder spreading process, actually it is important. It determines the packing density of a powder layer. It directly influences the interaction between the powder particles and heat source, therefore affecting the properties of finished part. In the selective melting and electron beam selective melting processes, dense powder layer makes the fusion more steady. Actually, why we want dense? Not only to have a dense part, but our fusion process, the interaction of the energy source with the powder becomes quite stable and steady. And we reduce the defects like balling, shrinkage, and pores kind of defects. So there are many effects like when powder is laid on the powder bed, there are many things which play a role. Just I'll give you a glimpse of it. I'll not go in details of this thing because it is more towards powder metallurgy related. The first thing what came out, which was really interesting, is that this is a rake or a recoater, and there is a powder heat. If powder heat height is changing, whether powder density change, that bed density changes, they found that it has no relation with the powder heat height. The powder bed density is independent of height. So there is whatever height we are playing with has no role on the powder density. And there are another point is that wall effect, like top rake is moving at the bottom build platform is there. So some powders which are hindering these two walls will be pushed away. So due to the rake and base plate, they causes the porosity in the bed. This is the contribution of which increases with the increasing the particle size. If my particle size increases, then the wall effect contribution will be there, which will lead to lower density and the lower packing density. Then there is a cohesion effect also, when the powders will agglomerate, and this tendency is more in the finer size. So all these studies have been done by researchers, and I'll just come to the final conclusions. The guidelines which has been drawn from these studies are that commercially feedstock of SLM follows a Gaussian distribution, and existing results have established preliminary powder requirements suitable for SLM processes are that D90 by D10 ratio should be less than 19, D50 by D10 should be greater than 10, and D19 layer, most of 90% of the particles should be having a diameter less than thickness of the layer. So this is the criteria which has evolved. In powder bed fusion, AM relative packing density generally is in the range of 40 to 60%. and reducing voids in the coarse powder matrix by adding fine size particles may not be a practical solution for SLM, which was widely used and is being used in powder metal. Is not a practical solution because of the many effects which people have studied. The powder particle size below 30 micron tend to exhibit clustering behavior due to cohesion and antiparticle forces. The powder flowability becomes more restrictive and with decreasing the particle size. So what we want is powder should flow, packing density we want highest. So because of that, finer particles which have a tendency for clustering or accumulation problems. So now we know what should be the preferred powder size. Now we can come now what are the parameters which are important. So actually for building AM process like powder bed fusion, what exactly we are looking for? We are looking for density, and I have written 99, maybe 99.5% of higher dense product. Surface finish should be good. Of the order of 10 micron generally we can get easily. Then residual porosity should be less than 0.5, and length scale of microstructure, we want fine microstructure, and deposit should be free from cracking, swelling, and delamination. So there are parameters which are laser dependent, powder dependent, machine dependent. So like which are important, I'll just mention that the power, laser power, scan speed are really two of the very important parameters, and then there are then there are spot size. Scanning studies are also equally important. Powder characteristic, generally we go for flowability and apparent density checks and particle in relation to the particle size distribution. And machine has its own parameter like positional accuracy, atmosphere, decoder blade, and laser power calibrations. These are the few important things for machine. So there most of the many things are predefined. Powder characteristics. Once we have said about powder characteristics are predefined, spot sizes predefined, gas flow rates are generally predefined, build or orientation is predefined. once we start build, all these things are predefined parameters. Then something we need to monitor and control: the layer thickness, laser power, scan speed, hatch distance, scanning strategy. Some of these things we'll discuss in subsequent slides also. So here, just one more thing I wanted to just inform is that the scanning strategy, when laser is scanned in in a plane, say nth layer, it has gone scanning in this direction as shown here. The next layer scanning is turned by 67 degrees to the previous scanning direction. So this change in the direction actually provides provide isotropy in the properties. It removes the anisotropy in the deposit. So this is how a study has been has brought out that if orientation of scanning is changed by 67 degree from previous layer, and we keep on doing that, then we can control the anisotropy in the AM deposits. So now we have learned the parameters. We have learned we have learned about powders and all. Now laser has a very interesting thing. What we want actually, when we are exposing the material to the laser, we want material to absorb that laser. So the data, most of the data which was available was for the solid materials, means solid materials. So not for the powders. So in a powder bed, how the absorption will be. So it has been found that as this SLM process started with the CO2 laser, that is a wavelength of 10.6 micron. If you see the figure here, that CO2 laser falls here. The absorption, if we use CO2 layer, the solid metal absorption is shown here as a mild steel, stainless steel, moly, aluminum. Aluminum, hardly there is any absorption. It's 2%, 3%. Most of the CO2 laser will get reflected from the aluminum. Stainless steel also around 5% absorption is there from the solid piece. So when SM started this CO2 laser, that was the reason it was not possible to deposit aluminum, because it was not possible. Aluminum was not absorbing enough quantity of laser. Then it was changed to niobium YAG, and then ytterbium YAG fiber laser. When it became ytterbium fiber or niobium and ytterbium fiber laser, that quantity on absorption on aluminum and others increased, but still we see the copper, it is very less. So whether it is possible, but all these data are for solid piece. So we want to know how the powder bed behaves. So what was found, that powder bed gives more surface area, so absorption is far better than dense material. So that way, like copper, if you see the copper with the fiber laser, you can with the 1.06 micron wavelength, its absorption is around 60% of the laser energy it will be able to absorb, whereas dense material absorbs only 10% of them. So we saw one advantage is using powder bed, that yes, absorption of the laser is far better, and it is good for fiber laser. How the laser interact with the powder? So depending on the power and the scanning velocity, different types of defects can form in the deposit, and it all depends the interaction of the laser with the powder bed. It can be balling, keyhole, or lack of fusion. So this is a laser power and scanning speed. So if my power is lesser, scanning speed is high, we will end up in lack of fusion. If power is very high and speed is lower, a lot of energy we are pumping in, so it will lead to a keyhole formation. This is the operating window where we want to confine ourselves. And if my power is high and speed also is high, we can end up in balling effect. So this here I'm showing the balling effect. What happens when laser energy is very high and speed is high, that actually laser is moving in a line, so we are creating a liquid line actually, and this line becomes unstable. It's a Rayleigh's stability criteria. It is similar to that, like water falls from a tap, and if we narrow down the things, that continuous stream divides into small droplets. So same way here it happens. The Rayleigh's instability comes into play, and we end up instead of a single continuous track, we'll end up in a formation of balls or droplets, which will hinder the subsequent builds also. There are remedies. All remedies are related to controlling the power and scanning speed. So there is another thing. If my energy is not sufficient, so I'm not able to melt fully, so there will be an unmelted zone. It'll lead to a lack of fusion. So we have to optimize in the thing. And if my power is too high for a given speed, we can end up in a very deep melting zone, and which when because energy will be so high that some evaporation will happen, and when this liquid pool gets collapsed, this evaporation and this vapors will get encapsulated, and there may be a keyhole formation. This is why there will be a pores because of keyhole formation. Okay, so these are the laser powder interactions. So just to understand that how much energy is required for melting for a given layer thickness, and that how to estimate that. So just I have made a small graphic presentation. So this is you assume that the three circle here. This whole thing represent a single layer thickness. So when we melt, suppose laser has passed and melted a particular zone. So when we melt, we form a dense part. So it leaves a gap here. So there is nothing here now. So we have a powder here liquid metal which are solidified, and there's a powder. There is nothing here. So when the next layer comes in, so powder comes here also. right? So now next time when a laser has to come here, it has to melt not the one layer, it has to melt more than a layer, powder more than a layer. Also, it has to melt base part of the base metal so that there is bonding can happen. So it continues. Now, when it is melted, so now we have unmelted zone, which is more than a layer, more than one layer of one layer of sphere. Okay. So now again, laser has to melt this much of powder and base of it. So this much amount of energy will be required. Then we come up in 1.5 times the thickness powder layer height has become, instead of one powder layer, it has become 1.5. And now laser has to melt 1.5. So this way it continues. Like when I plotted it with the layers, what will be the thickness of the powder which laser has to melt, assuming that density, powder bed density is 40%, 50%, 60%. When I plot it, I find that in the first condition, if we take, laser should have a sufficient power to melt approximately 2.5 times of the layer thickness. So if it is, so now, most of the powder bed fusion, the energy of the laser, or the parameters are selected in such a way that they are able to melt approximately 3 times the layer thickness. So this basically is to get a sound deposit, to ensure the bonding between one layer to another layer when deposition is happening. So no, actually the important parameters generally, which when we talk about process optimization, mainly 3 parameters which are really important are laser power, then scan speed, the speed at which laser scans the build platform, and then the hedge spacing, means the distance between first scan to next scan. So these are the things which are shown here. So this is a hedging spacing. So this is the first scan, and this is the next scan. So this distance between the center or to center of this thing is a hedge spacing. And these are the parameters which we have to finalize. And layer thickness and all are generally fixed for most of the processes. It will be 40 to 60 micron. And so we have to finalize what should be the laser power, what should be the hedge spacing, what should be the scan speed, so that we can get sound deposit, we can get required microstructures, and which can lead to a component meeting all the requirements. So there are some thumb rules, which are used to optimize the process parameter. So I'll try to skip this, because this is it'll be too much of detail, because it is based on some analytical models, and yeah. So I'll come to the one simplified model which very innovatively people have used. Actually here, what the people did is that they estimated the melt pool when a laser the melt pool. So this can be estimated experimentally, as well as Rosenthal equation is there. With that we can estimate. So once that, by writing a simple codes in Python and all, so people have done it, and they this is a like laser track, how it will be when it is deposited based on the estimation of melt pool dimensions. And then next layer which next scan will be at 67 degree. So then again cross section of that is plotted using Python program. With that, by changing the process parameter, from the equation we can find out what are the dimensions of the melt pool, and by changing the hedge spacing you can model it, and you can predict what is the where the unmelted zone will be and which condition will lead to fully dense product. So these are very simple techniques people have used to resolve the issue of optimization because it's a very complex task. We have done a similar simulation in CAD, this thing, wherein what we wanted to show is that when we are depositing when we are depositing liquid and subsequent layer, it is angle is changed, scanning angle is changed by 67 degree. So you end up, and we know that laser will melt at least 3 layers. So what we will find out the zones which are melted 2 times. There are zones which are melted 3 times and zones which are melted single time. So we wanted to know if such zones, whether there is a change in the any change in the properties. So we did some hardness check and all, and we found that hardness are almost in some range, and there's not much of a change in the hardness point of view. And microstructural also, we didn't find too much of variation. So it gives a fairly uniform microstructure. Okay, this is same towards parameter optimization. Probably for this audience it may not be that useful, so I'll skip this portion of my talk. Okay, in addition to parameter optimization of parameter, particularly what we have talked about or what I wanted to communicate is that laser power, scan speed, and head spacing. There are many other important points which we have to take up. We have to consider while defining the process, and this is like part geometry. If it involves thinner walls sitting over thick portion sitting over thinner walls, it generally lead to heat buildup because heat will not pass through. So these kind of problems can locally change the thermal gradient, and this may lead to residual stresses and all those things. So we have to find a solution from part to part. We have to find a solution, like generally this kind of problem solution lies in heating the bed to reduce the thermal gradient. There are many things like overhangs. If overhangs, bottom portion of overhangs is supported by powder. So if overhangs are because powder will not have that good thermal conductivity. So what will happen is that cooling rate will be slower there. So those things there will be some change in the microstructure there. Some properties change may be expected. So these things we have to tweak with the parameters. There it can be like we may intentionally come up with a lower laser energy. So local there is a global parameter and there is a local parameter. So we have to come up with a specific parameter for solving the local problems in a component. So this also happen, and this is being done by all service providers, which in many of the cases we will not be aware of it. So then there is a thermal fluctuations. This during SLM processes, we know that there is a repeated material undergoes liquid, then solidification, then again laser comes and melts part of the layer, or if it is not melted, then heat from the liquid above will be coming to this material. So there is a thermal cycling, it goes, and it leads to residual stresses and build cracking. They are very common problems, and people have to struggle to resolve these issues. So many of the stress relieving solutions are the stress relieving treatment, residual stresses by 70%. Laser scanning is another technique which is employed to reduce the residual stresses. Preheat of bed, as I told earlier 40%, and there are scanning strategy also you can change to reduce the residual stresses. This is a microstructure of one of the sample, one of the print what we have done long back. This is the aluminum. You can see the laser tracks, and you can see here. This is the previous scan, and there is 67-degree next scan. So laser tracks are very clearly visible, and there's the orientation of 67-degree goes. The hardness we have checked, and we didn't find much of a thing. It is well within ±5, which is very common in some material. Very interesting thing is that the kind of properties what we are getting is far better than what we can get with the conventional processes, and it gives. I was a bit surprised because it was aluminum, and aluminum generally forms a very oxide layer on the surface very fast. So, but in spite of that, what we found is that even ductility is very good as fabricated, as printed condition. Then subsequently, when we devise a heat treatment, different treatment it gives you a flexibility. Like if you go for different combination heat treatment, you can compromise with the strength, but your ductility comes very good, 18% you can get. So this kind of freedom you get in AM, that is available. And then here is like topology optimization. Okay, it was not part of my. I never wanted to cover this particular thing in this talk. So, but just I'll give you a glimpse of it. Like this was a actual what we designed generally. If we optimize the topology, and we can gain on the stiffness or mechanical wherever it is required, material is added. Actually, concept of topology optimization is you have to define the properties for which you are optimizing. And wherever material is required, there only you add it, because the conventional processes, they don't give that kind of freedom. So our products are over designed, but AM gives you that freedom. So you can optimize it, you can reduce the weight, you can make your design more functionally more robust. So, and these are the capabilities exist. So what are the advances happening? One of the advances which has really impressed me is that support-free 3D printing. Velo 3D, one company, has come up with a unique this thing, whereas they can print parts without any support. This is really interesting. Then there are people coming up with the artificial intelligence software for monitoring the 3D printing during the process, so that we know if there is something goes wrong in the process, we can capture it. There are the feedback controls are being developed. Actually, is it possible that when printing is happening, something goes wrong, feedback comes and process controls it? So this will make a process like free from all trouble. So, but it is still under development. In situ inspection is another, because when you print a complex part, inspection becomes really more complex. So we cannot go with the conventional inspection methodologies, because it will defeat the whole gain what AM gives you. AM delivers you component fast, but when you go through conventional qualification means, it takes so much time that it defeats the whole purpose. So there has to be techniques or in situ inspection technologies which are being developed. Body structure, like shape memory effects, some thermal conductivity effects, and all those things are, it is possible to design, and people are doing that. And there is a selective powder. This thing now, people are developing techniques wherein you can deposit different powders. So you get a control on the voxel. Like pixel is in 2D, voxel is in 3D. So you can control the material in a voxel. What kind of property you are requiring in a voxel, that up to that level control is being attempted through AM. So challenges ahead are like benchmarking the capabilities of the process in terms of design, developing integrated in-process sensing, monitoring, and control. This is really important if we want to go in a big way, because qualification of parts are really important for aerospace. Smart structures, 4D printing, new materials, latest structures. There are a lot of opportunities in this area. Microstructure modeling is another area where many people in India are working, many labs are working, and post-processing is a challenge because surface finish in complex part, if you want a good surface finish, then post-processing is an important thing. Alternative to conventional qualification methods, we have to find new methods, as I told earlier. And so what kind of part we should select is generally complex part which has high lead time, or assembly which require a lot of welding, assembly which require fasteners and all, or repair of parts. These are all things where AM can immediately easily can be switched over to, and we can directly go for it. So with that, I'll thank you for your patience listening, and I'm open to questions.
Thank you very much, sir, for such an enthralling and captivating lecture. I'm sure this lecture has helped our audience to enhance their knowledge in the trending field of additive manufacturing. Now it's time when our audience can ask their queries related to this topic. Our YouTube viewers may also ask their queries through YouTube chat box. So we'll go through these questions one by one. So any of you, if you have a query, please ask. The Google Meet also they can ask questions, and YouTube viewers may ask their questions on the chat box. Please ask your question.
Yeah, good morning, sir. This is Pulkesh Desai. Am I audible?
Yes, Pulkesh, boliye.
Yeah, thank you, Dr. Govind, for a very nicely structured lecture, sir. I have one question. You talked about in aluminum components the effect of thermal cycling. Could you elaborate it a little better, sir? Like what kind of improvement in the properties are observed by, say, subjecting a component to thermal cycling post it is built?
Okay, see, basically, what I mean to say is that when component is being built, suppose you are printing nth layer. So when you are printing nth layer, n-1 layer is already solidified at it is at some temperature T. So when you are building nth layer, the heat from nth layer will pass on to n-1 layer, and its temperature will increase. Then when you are printing n+1 layer, again n-1 layer, some heat will come and it will again go in some cycling. So this is a thermal cycling which different layers or the components are subjected to in the process. And this actually, depending on the material to material, there is a variation. Like in aluminum, generally there is no phase change, so at the most only coarsening of the microstructure can happen. But in some materials like titanium and all, there are phase changes, so it will have its own effect on those materials. So that is the point actually. In materials where there is no phase change, there is some coarsening can happen, or if there is a phase change, then those phases will change depending on the thermal cycle.
Thank you, sir. One thing which we have observed is in aluminum components, as you rightly pointed out, we have seen improvement in the mechanical properties of the additively manufactured component vis-a-vis say the normal alloys which we receive as the wrought alloys. So how do we correlate it, sir? What may be the reason for the improvement in the properties?
Which material you are talking about?
Aluminum alloy. Say if you have got for
ALS.
10% ALSI,
Yeah.
ALSIs.
Then you compared it with which material?
Sir, 6061, sir. ALSI 10 mg with
Yeah.
6061.
So you are saying that ALSI 10 mg gives you better properties than 606?
Yeah, yes, sir. Yes, sir. Yeah.
So basically, you see here, you see that these alloys are different. ALSI 10 mg is basically coming from the cast material. 6061 is difficult to print, 3D print actually. So for printing 6061, generally you have to have some additives like titanium boride, or some people are working on it. So this ALSI 10 mg, is giving you good properties, because here the material, when this laser is scanning micron size, a few hundreds of melt pool of width, few hundreds of micron, and it laser moves in 100 to 1 meter per second velocity. So the energy input to this micron thin layer is imparted by laser, and it solidifies very fast. So solidification is rate is 10 to the power 3 to 10 to the power 6 Kelvin per second. So this fast solidification rate observed in the process impart the refinement. This refinement gives us the gain in the properties what we are observing. By conventional method, if we process this alloy, we cannot get these kind of properties. So comparison mainly what my observation has been that if you compare with the cast alloys, AM alloys are far better, but if you compare with wrought alloys, they are equal. They are not very inferior, they are equal. Or some cases may be better, but mostly they are equal. Yeah.
Thank you, sir. The properties are almost say 5 to 8% better, not a way
Okay. I
very
mean,
good.
6061, I have to see because right now I
Yes, sir.
cannot comment on that.
Yeah, thank you, sir.
Dr.
Thank you
Govinda,
for
very
your answer.
Dr. Govinda, this is Anand Pathak here, SSME President. Wonderful informative talk by you and very detailed process parameter you have explained. That was really wonderful. Even I myself have worked with Dr. Bhanu Pant Sharma ji, Dr. Khandra for powder metallurgy years back. But these some of the new things you are giving insight, like the smaller the particle size, and you are getting the lesser density of the entire product of powder metallurgy. So some of the new things are coming up through. It's really wonderful, very informative, sir. Thank you, sir.
Thank you. Thank you.
Thank you very much, Anand Patak sir, for your words of motivation. And again, thank you very much, Govind sir. So we have few more questions here. One question is, are there any SLS or SLM 3D printing carbon fiber or graphene manufacturers in India? Hello? Am I audible?
Yeah.
Yeah, sir.
Audible.
One person wants to ask a question. He asked whether are there any SLS or SLM 3D printing carbon fiber or graphene manufacturers in India?
SLS or SLM.
Yeah.
I'm not sure, but FDM people are there. Okay. FDM, with this people are printing. One has to check. There's a company in Mumbai, Divide by Zero, and there's a company Sri Rapid. These Imaginarium, Sri Rapid, and Divide by Zero. I mean, these people may be able to help you out.
Thank you very much, sir. Then Ashok Munia, he is asking what type of inspection technology are required for these processes. What type of?
See, at present, at present the inspection mainly is being most preferred is CT tomography. But in my opinion, I mean, we have to go for something is based on analytic data analysis based. So you can get plenty of data. Like there is one simple technique is like optical that thermal imaging. When laser is scanning each layer, you get voluminous data in terms of thermal imaging. People have come out using that thermal imaging data. They can predict where the parameter has changed, where parameters has fluctuated, and that correlation one can establish that if there is a fluctuation in the parameter in the part what has happened. With that thing, people can predict, yes, this zone is likely to have some issue, and people can concentrate only on that zone. So like these kind of techniques we have to come up. So generally now at present what we are doing is radiography, UT wherever is possible, and the CT tomography. There's standard conventional NDT techniques are only followed, but I feel there is a lot need to be done in this area, particularly. It should be analytical piece.
Thank you, sir. Any other question if somebody wants to ask? Sir, I have a question. As you said that there are thermal fluctuations, and you talk about the laser rescanning with same parameters. So, sir, how do the laser rescanning with the same parameters help in solve this problem of thermal fluctuation?
No, laser rescanning is not same parameter.
So what type of how it is
actually,
done, sir?
For controlling the residual stresses, what they do is, suppose it is kind of previous layer is preheated. The layer what you are suppose the layer what you are printing, the layer what you are printing is preheated by laser first, so it doesn't use the same parameter. There is some disturbance coming.
Yes.
Patak sir, can you mute your mic, sir?
Okay, so basically what it is done is that powder bed is first scanned with the laser. So when you are scanning with the laser, your energy and parameters are such that you are not melting it, you are just kind of preheating it. And then the second scanning is actual scanning where you are melting the layer. So this is called laser scanning technique, by which you can control the residual stresses.
Okay, sir. So, do we have any other question? If not, we shall move further. One of our YouTube viewers is saying that powder metallurgy is his core subject and he wants to coordinate in this work. I don't know how it can be done, but one of our YouTube viewers has put his comment on the YouTube chat box.
No, I mean, Ankit, I didn't get you.
Sir, one of our YouTube viewers, he has put it in the YouTube chat box that his core area is powder metallurgy and he wishes to coordinate in this work. So I don't know how it can be done. So you please, if possible, you can throw the light on this.
I think he should contact Dr. Khanra at VSSC. Am I right, Govindaji?
Yeah, I mean, okay, powder metallurgy, it is, this area is basically open to all. I mean, not only powder metallurgy, this even building people can work, and total metallurgy, it is there. So, yes, how to collaborate, I mean, he has to send, which institute and all that detail, probably then we can have a look. That's our point.
Right. So,
okay.
If there is no further question, I think we'll move further. So, we'll have another very interesting.
Yes. Proceed.
Yes, sir. So, we'll have. First of all, thank you very much, Govind sir, for such a scintillating and dazzling lecture and for such a knowledge enhancing question and answer session. Thank you very much, sir. On behalf of SSME and on my behalf, thank you once again. So now we would like to have one more interesting presentation from Altair team, who are also the sponsors of this webinar series. So we have Mr. Vishal Bagdadia with us, who is Assistant Technical Manager in Altair. He is a graduate mechanical engineer with 4 years of experience in research and new product development in automotive, defense and aerospace industry. Currently, he is working as Assistant Technical Manager for Altair Simulation Suite and Design Tech Systems. He has hands-on experience in FE modeling, concept generation, structure analysis, lightweighting and manufacturing simulation. So I welcome Mr. Vishal Bhattadia to deliver his talk on simulation-driven design for additive manufacturing. Mr. Vishal.
Thank you, Ankit. I hope you can hear me. I'll just share my screen.
Yeah. Please go ahead.
Yeah.
Yes.
Yeah. Do let me know if the entire screen is visible so that I can proceed.
Yeah, you
Yes.
can
Yeah, all
proceed.
right. Uh, Yeah. First of all, thank you, SSME team, for providing us this platform for us to present this. And Dr. Govind, a great session on additive manufacturing. So, to just give an extension on that, I'll be speaking about overall simulation aspects when it comes to additive manufacturing and also the design aspects of it. So, to start off with, when we talk about lightweighting and increasing performance with respect to additively manufactured structures, the primary motivation for lightweighting is to reduce the material, which leads to a faster and easier printing as well as lowering the overall cost. And when it comes to the design aspect and how we can complement design with additive manufacturing, we can make use of either lattice structures, topology optimization to enable these light weightings, which would complement the additive manufacturing process, as well as we can carry out assembly consolidation to reduce number of components and consolidate into, let's say, a single part. Turn a 30-piece component, a 30-piece part into a single part. So, what I would like to mainly discuss is what is Altair's point of view when it comes to design for additive manufacturing and how we provide the simulation platform to carry out those. So, I'll talk about mainly two approaches and the overall process to complement that. So, to start off with the topology optimization approach, so we offer a platform to carry out topology optimization, and the typical workflow to carry out any optimization process in the platform that we provide starts right from taking a base model, understanding its overall design performance, and understanding what is the overall scope that you have to carry out the lightweighting. You can further develop the overall package space for it, and then carry out the optimization by doing various iterations. You can control the manufacturing constraints, you can control the overall shapes that you want to generate, and once you do that, we also provide the platform to carry out printing process simulation, and then finally reiterate and carry out the overall performance check. In this case, we take care of all the design fine tuning, surface generation in terms of making a smooth surface for the final product, and then taking it for production. So the topology optimization is also complemented with the overall control that we offer in terms of manufacturing processes. So we can control the member thicknesses, the draw direction, extrusion, but primarily when we talk about additive manufacturing, we can control the overhang of the design. So we can predefine the overhang angles that we want to establish for the design so that we get no support in terms of the final process. So as we can see, when we carry out topology optimization, different design concepts based on different manufacturing constraints you apply, you would lead out with a different design out of it. So to talk about primarily the purely additive manufacturing process that we can use with the overall topology optimization, I'll just take up an example of one of the antenna mounts from Ruag, wherein they took a base CAD base design, which was originally of a structure which was bolted made of aluminum. They carried out they generated the overall package space for it. They carried out the optimization of it, and based on that, the design interpretation was done. Once the design was generated out of it, the geometry was created using something called as polynodes that we offer. Polynodes is nothing but a smooth solid modeling that can be done over the original topology optimized design that you have. So you can generate a completely smooth surface model out of it, and once that was done, the design was evaluated and the geometry was validated, and it was manufactured, leading to overall reduction of around 43% mass and also increase in the frequency. Another similar case was done with Ruag and an Israeli aerospace company for a moon thruster bracket, wherein again the original design was understood and analyzed, wherein it was around 4 kgs having a frequency of 80 hertz. The optimization was done to find out what is the design tendency and which one is more convenient in terms of manufacturing, and a feasible design was chosen. Once that feasible design was obtained, it was polynobed to make a smooth surface out of it. It was identified like how it can be split. Once that was done, the overall structure was manufactured, and we understood that there was a significant reduction in mass as well as increase in the frequency. So the frequency went from 80 hertz to 350 hertz, the base frequency, as well as the mass was reduced from 4 kgs to 2.9 kgs. Another approach that we talk about in terms of complementing design and additive manufacturing is lattice generation. So we do offer lattice generation, and the main primary motive of lattice is to drastically reduce the mass. You can get better stability, you can get better thermal behavior as well as design characteristics. We have two approaches when it comes to lattice structure generation. The first approach is the tetrahedral approach, wherein what we can do is we can take the structure, we can define the lattice parameters, be it the lattice length, the lattice diameter, and based on, and also the fill ratio. And based on that, what the tool will do is it will first of all analyze the model. It will understand which are the stress concentration regions, and based on that it will decide which regions should have what kind of a lattice. So this one is not just a dumb fill lattice, it is a lattice based on the structural performance. So the overall result that you get out of it is better suited for structural performance out of it. Another approach that we have is something called as the poly mesh lattice. In poly mesh lattice, what we have is a freedom of generating different shapes of lattice, not just restricting it to tetrahedral. We have different types of unit cell lattices available, as you can see in front of you. And what we can do is we can first of all take a model, generate a poly mesh out of it, or generate this unit cell lattice, and then take it for analysis. And based on that, we can tweak the performance or tweak the parameters of these lattice structures. So apart from the design aspects that we have looked into, be it the topology or be it the lattice, we can take that forward to get a better understanding of the process simulation as well, by also enabling printing simulation in the same platform. So typically the need for printing simulation is to avoid the failures and restrictions in the geometries, to understand what are the risks, and to also understand in case if there are some drastic thermal deformations in that. So to take care of that, we have a process set to also simulate this in terms of printing, wherein we can select the part, we can make the configuration of the printers, we can orient our part, we can generate the support inside the software itself, we can preview the slicing, we can directly export it out for printing if it is suitable, and we can run a thermomechanical simulation. So when we talk about what type of printers we support printers from EOS, SLM, Renisho, as well as you can have user defined aspects of it. We can generate different types of support, be it a pin type, tree type, block, and so on. The materials, we have a default material library which can also be customized by giving the various physical and thermal properties. And when we talk about process parameters, we can set the parameters of the printer, be it the velocity, the laser power, powder thickness, powder absorption, cooling temperature, and so on. And currently we offer the layer by layer strategy, but in one direction. And when we talk about the thermomechanical aspects, we can check out the displacement, strains, null temperature, so we can mainly check out the spring back and also the pre-stresses in the structure. So just to tell you about the approach that we use, what we do is we have something called as a voxel mesh that gets generated out of the structure. And what we do is we take one layer of the mesh, we understand its thermal performance, and then we activate the next layer. And based on that, the conduction between the layers as well as the outer region and as well as the convection gets taken into consideration, where one layer will get activated, the other layer will get cooled, and the next layer will go on and on. So by the end of it, the overall thermal mapping will be done, as well as the spring back will be understood once the support gets deleted from the structure. We have verified the printing simulation that gets simulated in the software with the actual results, wherein we have gotten a very good correlation with the physical data. And we have also enabled it for optimization, wherein the original design had a lot of support structure because of the overall um, overhangs in it. So that was removed out using the overhang constraint that we got. We generated a self-sustaining structure which reduced the support drastically, and then it was also correlated in terms of the printing performance of it, and where we observed a significant match in terms of the displacement that came in the actual model with the printed model, that the printing simulation model that we have. So this is just the part and the reason. So there are several correlation studies that we have done with various automotive, aerospace, and also printing companies. So to just summarize all of these, the promise of additive manufacturing in terms of design aspects would give, first of all, the geometric freedom to uh, go more towards the lightweighting approach, as well as and part consolidation, and it would also accelerate the product development and give the design individuality. So with that, I would like to summarize I would like to close my presentation. And once again, thank you, SSME team, for providing us the platform to showcase our simulation platform for design for additive manufacturing. Thank you. So if there are any questions, I'd be happy to take it.
If there is any question from the audience, you may please ask Mr. Vishal. So, if there is no question, uh, we have come to an end of this interesting program. So I would like to thank you very much, Mr. Vishal, for such an interesting presentation. I'm sure our audience is overwhelmed with the information about how innovatively Altair team is working in the field of additive manufacturing. I pay my sincere thanks to Altair for sponsoring the SSME webinar series 2021-22, current trends and advances in mechanical engineering for space applications. I would like to thank Anand Pathak sir, President Space Society of Mechanical Engineers, for all his guidance and motivation. I would like to thank Shri K. Desai sir, Vice President SSME, for extending his support to this lecture series. I would also like to thank Shri Ashish Soni sir, the vibrant secretary of SSME, whose efforts are always profuse and enormous. I thank all the executive committee members, without whose continuous support, organizing this lecture series will not be possible. And in last, I once again would like to extend my sincere thanks to Dr. Govind sir for such an interesting lecture. Thank you very much, sir. And I would like to thank all the audience at Google Meet and YouTube to come and who have come here and listen to this program. Thank you very much. So, if we don't have any further question, we would like to conclude this session. Thank you very much to all.
Thank you, Dr. Govind, and thank you, Vishal.
Yeah, thank you, Ankit.
Thank you, sir. So we'll conclude this session. Thank you.